Cambridge Assessment Admission Testing, 6th Term Examination Paper, Step 2019, Paper 1, Mathematics 1, Code number 9465, Section A. The link to the question paper is in the description below. Hi, I am Babak Majidzadeh Garjani. In this video, I am going to solve the first problem of this past paper related to a STEP exam. Let me read the question for you first. I read it part by part, okay? A straight line passes through the fixed points 1 and k and has gradient minus tangent of theta, where k is positive and theta lies between 0 and pi over 2. Find, in terms of theta and k, the coordinates of the points x and y, where the line meets the x-axis and the y-axis respectively. Okay, let us stop here, solve this part. So, in the first part of this question, you are supposed to find the coordinates of capital X, the x-intercept, and the coordinates of capital Y, the y-intercept. Okay, if I want to find the x and y intercepts of a given line, first I need to know the equation of that line. Yes? Okay. But before doing that, let us try to sketch a graph for this solution, okay, for this problem. Assume that this is the y-axis, assume that this is the x-axis, yes. So here is my y-axis, here is my x-axis. Okay, and if you see, k is a positive number, so if I want to, for example, locate the point with coordinates 1 and k, so let us consider that this is 1, and let us consider that this is k. K is positive, so that's reasonably correct. So this point would be the point of 1 and k. My line is supposed to pass through this point, and the gradient is given to be minus tangent of theta. On the other hand, theta is given to be in the first quadrant, and we all know that the tangent in the first quadrant is positive, so minus tangent of theta is negative. So it means that I have a line inclined like this. So that I am drawing right now is a reasonable sketch of that line. So for example, you can assume that this is your line. This line is a line with a negative gradient, of course. And then what we know is that this point is the x-intercept, and this point is the y-intercept denoted by capital X and capital Y, and we're supposed to find the coordinates of capital X and capital Y. But before that, we need to find an equation for this blue line, okay? On the other hand, every one of us know that how to do this. We know that y minus y0 equals to m times x minus x0 is an equation for a line, for a straight line whose gradient is m, and then which passes through a point with coordinates x0 and y0. So it's easy to calculate everything here. So I have y minus y0, I put the y coordinate of my point, which is k, is equal to, instead of m, I put the gradient, which is given to be minus tangent of theta. X minus x0 is the x coordinate of the same point, which is 1 here. Okay, so that would be an equation representing this blue line for me. Okay, if I want to find the coordinates of x, I need to put y value equal to 0 and calculate x. Okay, so I put y equal to 0. What do I get is 0 minus k is equal to minus tangent of theta times x minus 1. I am supposed to find x, so I divide both sides by minus tangent of theta. So it becomes minus k divided by minus tangent of theta. It's equal to x minus 1. But am I allowed to divide safely by minus tangent of theta? I would say yes, because as you know, it is mentioned that theta is in the first quadrant and it is not equal to 0, it's not equal to pi over 2, so it means that tangent of theta is a non-zero number. So minus tangent of theta would also be a non-zero, so I can safely divide both sides by minus tangent of theta. Okay, and then now this minus sign and that minus sign cancel, and I bring this tangent theta up here and make it to a cotangent and change it to a cotangent. So then it means that k cotangent of theta is equal to x minus 1. So then immediately x becomes 1 plus k cotangent of theta. Yes, so this means that the point x has 1 plus k cotangent of theta as its x coordinate, and of course 0 as its y coordinate. Yes, so let us keep it. Similarly, for finding the y intercept, I need to put x equal to 0, and then so I put y equal to 0, x equal to 0 here, then here, and then what I get is this. So y minus k is equal to minus tangent of theta 0 minus 1. But then this becomes positive tangent, and I move k to the right hand side, so it becomes k plus tangent of theta. So what can I write is that the point y has x coordinate 0 and y coordinate k plus tangent of theta. Okay. Now we can move on to the part I, the first part of the problem actually. Okay, so let me read this part for you. Find an expression for the area A of triangle OXY in terms of k and theta. And it is mentioned that the point O is the origin. Okay, so let me just write this O here on my picture. So here, my figure, this is O, and we are supposed to find an expression for the area of this triangle OXY. This is the triangle. It's a right angle triangle, and I want to find the area of this triangle in terms of k and theta. Okay, now I can do it. So part one of this problem is the area that I am supposed to find is 1 over 2 the length of the line segment OX multiplied by the length of line segment OY. But then this is clear that the length of line segment OX is exactly the x coordinate of the point X. So it is equal to 1 plus k cotangent of theta multiplied by OY is the y coordinate of point capital Y. Yes? So this is A. And I think it would be easier if we multiply these two brackets. So then it becomes 1 over 2, it is k plus tangent of theta plus k squared cotangent of theta. And then you can see if I multiply this term by that term, because cotangent multiplied by tangent is 1, so I will get just k. Yes? And then I can combine this k and that k, it becomes 2k, and then I multiply this 1/2 inside. So what I get is this, is A equals to k plus 1 over 2 tangent of theta plus 1 over 2 k squared cotangent of theta. Yes, and now you see that the letters involved are k and theta, but k is a fixed value, so this is a function of only theta. Yes, so then it would be reasonable if I call it a of theta. Yes, So this is the formula, this is the expression of the area which was demanded in the first part of this problem. Okay? But of course, the first part of the problem is not finished yet. Let me read it again. You are given that as theta varies, A has a minimum value. It's guaranteed that A has a minimum value. Find an expression in terms of K for this minimum value. Okay, so probably the easiest and most natural way to tackle a minimum or a maximum problem is to talk about the derivative of the target function, here the area, for example. Okay, so what I do, I will start taking the derivative of this function a of theta. Okay, so let us do it here. So a prime of theta is equal to, the derivative of k is simply 0, and then I have 1/2. The derivative of tangent is secant to the 2 theta, and the derivative of cotangent is minus cosecant squared theta. So if you don't mind, so let me clean this and make it negative, and then I can just simply write cosecant to the 2 theta. Okay, and I would prefer to write it in a little different way. So I factor 1/2 and cosecant to the 2 squared out. Yes, so what happens, it becomes 1/2 cosecant to the 2 theta, and what is left in the brackets is is secant to the 2 divided by cosecant to the 2 theta minus k squared. Yes, so if you want to check it, just multiply this expression back inside. This cosecant to the 2 and this cosecant to the 2 will be cancelled, and I will be left with secant to the 2, which is exactly this one. Of course, I have a factor of 1/2 as well. And if I multiply this here, I will get this term back. So everything that I have done is completely valid. But it's easy to continue, so it becomes 1/2 cosecant to the 2 theta. And then instead of secant squared, I can put 1/cosine to the 2 theta. That's the definition of secant to the 2. And then I have cosecant to the 2, which is 1/sine to the 2. And then I have minus k squared. Okay, so then it becomes 1/2 cosecant to the 2 theta. And then this becomes sine to the 2 theta divided by cosecant to the 2 theta minus k squared. Yes, so here this will go and multiply by 1, this will be multiplied by 1, so I will get this expression. But this is very famous, this is just tangent to the 2 theta. So then it means that I have my derivative, so the derivative is 1/2 cosecant to the 2 theta, and then I have tangent to the 2 theta minus k squared. Okay, so far so good. Now, because I am looking for a minimizer, I need to put a prime theta equal to 0. So if I put a prime theta equal to 0, then I will get 1/2 cosecant to the 2 theta tangent to the 2 theta minus k squared is equal to 0. Okay, but you see that cosecant to the 2 of theta is never 0, so it means that this term has to be equal to 0. So that implies that tangent to the theta is actually equal to k squared, and it means that tangent of theta is either positive k or negative k. Yes, but theta is given to be between 0 and 0 and pi/2, if you remember. So it means that tangent of theta in the first quadrant is positive and cannot be negative. On the other hand, k is also a positive number. So the acceptable value is not minus theta here, is not minus k here, it's positive k, yes? So then this implies that tangent of theta is k, or equivalently, so theta is tangent inverse of minus k, okay? Okay, so you know that this theta, there is no guarantee for this theta to be a minimizer, yes? This, this theta can be a local minimizer, a local maximizer, or just corresponds to a terrace point. It's not clear yet, okay? Okay, but let me try to go a little bit around this problem here, even though this is not part of the solution of this problem, yes? Let me take this one with me to the next page. Yes. Okay, so let me put the derivative here in front of our eyes. Okay, so if you want to investigate this a little bit more, so do you remember the theta that I got is theta equals to tangent inverse of k. This part that I am describing right now is not part of the solution of the problem because here it is guaranteed for you that a has a minimum value, okay? But let me try to convince you that this is indeed an absolute minimizer. This theta is an absolute minimizer. Why? Okay, so here let me determine the sign of my derivative. So for example, consider this table. You have theta here, you have the derivative. This is your only candidate here, yes. And then you have pi over 2, and this is 0. You know that the derivative here is 0, okay? If theta is less than tangent inverse of k, since tangent theta is an increasing function in the first quadrant, this implies that the tangent of theta is smaller than tangent of tangent inverse of k, so which implies that tangent of theta is smaller than k. But then this means that tangent to the 2 theta minus k squared is less than 0. Okay? Now look here. This is a negative value. This is a positive value, this is a positive value, so it means that a prime of theta is negative. So here, the a prime of theta on the left-hand side of tangent minus 1k is negative. Similarly, you can convince yourself that on the right-hand side of this value, the derivative of a is positive. So it means that here on the left, the function goes down, and here on the right, the function goes up. So this is a local minimizer. This point corresponds to a local minimizer. And now we have another theorem that if we have only one local minimizer, that local minimizer is indeed an absolute minimizer. Okay? As I said before, this, what I just described here, is not part of the solution of this problem. Okay, now let us go back to the problem. Here, find an expression in terms of k for this minimum value. Okay, so I need to plug this value for theta, or equivalently tangent of theta equal k, into the function a theta and try to simplify that. That is a minimum value for me. So it means that I need my function. So let me go to the previous page, go here, and copy this function a theta here. Yes. Next page now. And then we put it here. Paste. Okay, here. Okay. Now I am supposed to plug this value, tangent of theta equals to k. I want to plug the value here, and what I get is a minimum. Okay. So let us do that. Yes. Of course, it is very simple now. If tangent of theta is equal to k, cotangent of theta becomes 1 over k. Yes. So now a minimum is equal to, I have k plus 1 over 2. Instead of tangent of theta, I put k. Instead of cotangent of theta, I put 1 over k. So then it becomes k plus 1 over 2 k squared multiplied by 1 over k. So it becomes k plus 1 half k plus this k, and that simplified, so it is plus 1 over 2k, and then what I get is k plus k, which is 2k. So it means that the minimum value for a is simply 2k. Okay, now let us go to the second part of the problem, part 2. Okay, let us read the problem first. Show that the length L of the perimeter of triangle OXY is given by this formula. L is equal to 1 plus tangent of theta plus secant of theta plus k times 1 plus cotangent of theta plus cosecant of theta. Yes? This is the expression that we want to prove for the perimeter of triangle OXY. Okay, let me go to the previous page. Here you see this was my triangle OXY. I am supposed to find the perimeter of this triangle. So I have to find the length of OX, which I already know. This is the length of OX. I also need to know the length of OY, which is clear. This is the length of OY. And then I need to know the length of XY, the hypotenuse of this triangle. So here, to find that, the most natural thing to do is to use the Pythagoras theorem and write xy to the 2 is equal to xy to ox to the 2 plus oy to the 2. Yes. So from here, I can calculate the length of xy. Okay, but I would need these expressions in the next page, so let me take them with me. So no, I will take this one. This is the OX value. Remember, so this is the OX value here. So this is my OX value. Let me write it here. OX is equal to that, the length of OX. And again, if we go back to this page, this is the OY value. So I go and paste it here. Okay, so this is my OY value. And then I am supposed to find xy value, which is to the 2. The length of xy is OX to the 2 plus OY to the 2. Okay, so let us calculate this first. Okay, the length of xy to the 2 is equal to the length of OX to the 2, which is 1 plus k cotangent of theta to the 2 plus the length of OY to the 2, which is k plus tangent of theta to the 2. I use quadratic rule here. So this is the first one to the 2. 1, 2 times the first one times the second one is 2k cotangent of theta, and the second one to the 2, which becomes k squared cotangent squared of theta. The second quadratic rule is k squared plus 2 times the first one times the second one plus the second one to the power of 2. Yes? Okay. Now this 1 here and that tangent squared theta at the end, I have 1 plus tangent squared. It's the famous formula, it's secant to the 2 theta. Yes? And then here, between these two, I can factor k squared out. So here, I can factor k squared out, then I will be left with cotangent to the 2 theta plus 1, but this is equal to k squared cosecant squared of theta. Yes, so then it means that this becomes plus k squared cosecant to the 2 theta. Okay, And then here you can see that I have 2k cotangent of theta. Here I have 2k of tangent of theta. So I can factor 2k out. Then I will be left with tangent of theta plus cotangent of theta. Yes. So far so good. Let us continue. So it becomes secant to the 2 theta plus k cosecant to the 2 theta plus 2k. And now I can write, instead of tangent, I can write sine over cosine. And instead of cotangent, I can write cosine over sine. Yes, so this becomes secant to the 2 theta plus k squared cosecant to the 2 theta plus, okay, I can take the common denominator. So the common denominator is cosine theta sine theta. Then it becomes sine to the 2 theta plus cosine to the 2 theta, which of course is 1. So it becomes secant to the 2 theta plus k squared cosecant to the 2 theta plus 1. Okay, I have a 2k here. Then I have 1 over cosine sine. But I can write it as cosine multiplied by 1 over sine. Yes, let me explain it again. So this one is just simply 1. And then instead of 1 over cosine sine, I can write 1 over cosine multiplied by 1 over sine. But then it is completely clear this becomes secant to the 2 theta plus k squared cosecant to the 2 theta. And then I have plus 2k. This part is nothing except secant, and this is cosecant. So then it becomes 2 times k times secant theta times cosecant theta. Okay? Now, if you look here, this is a complete square. You can simply write it as secant of theta plus k times cosecant of theta to the power of 2. So what does it mean? It means that the length of my hypotenuse is equal to secant theta plus k cosecant of theta. Good. Okay, so there is no plus and minus, by the way, because secant theta and cosecant theta and k are all positive. Okay, now the parameter L is OX plus OY plus XY. Yes, so this is simple to write now. So this is OX, which is 1 plus K cotangent of theta plus K plus tangent of theta plus secant of theta plus K cosecant of theta. Yes, but to make the formula exactly look what is given in the problem, here, let us look back. So I have this expression here, so I have to factor k out. There are terms with k, there are terms without k. So I combine them together, okay? So then what happens? L is equal to 1 plus secant of theta plus tangent of theta plus, now I factor k out, I have 1 plus cotangent of theta plus cosecant of theta. So finally we got the result. Okay? Now let us see what is wanted more here. Okay, you are given that as theta varies, L has a minimum value. Show that this minimum value occurs when theta is equal to alpha, where 1 minus cosine alpha over 1 minus sine alpha is equal to k. Okay? This is the another part of the problem. So let us take this one for granted this time, that the function has a minimum value. So it means that the derivative of my function calculated at alpha is supposed to be equal to 0. Yes? So here what I can do is to take the derivative of my function. So let me go to the previous page. So here I need to have my L in front of my eyes. So let me take this with me. Copy. Okay, so I would take the derivative, and at the end I have to insert alpha. This is supposed to be 0. Okay, so let me take the derivative of my function first. So L prime of theta is equal, the derivative of secant is secant theta tangent theta, plus the derivative of tangent is secant to the 2 theta, plus k. The derivative of 1, 0, the derivative of cotangent is minus cosecant to the 2 theta, and the derivative of cosecant is minus cosecant theta multiplied by cotangent of theta. And then I have to put this one equal to 0. Okay, so what can I see? It means that secant theta, tangent of theta, plus secant to the 2 theta is equal to, I move this part to the right so it becomes positive, positive. So it becomes k cosecant to the 2 theta plus cosecant theta cotangent theta. And then I am looking for k here. So k is simply the division of these two expressions, but here I can simply factor this out. So I can factor secant out here, so this becomes secant theta, then it becomes tangent theta plus secant theta, divided by here, I can factor a cosecant theta out, then I will have cosecant theta, and then I would be left with cotangent theta plus cosecant theta. So this is my k value, but let me simplify this as much as possible, yes? So if you write all of them in terms of sine and cosine, so this becomes 1 over cosine theta, and then you have sine theta divided by cosine theta plus 1 over cosine theta, and here you have 1 over sine theta, and you have cosine theta plus over sine theta plus 1 over sine theta. Okay, so if I rescale the numerator and denominator by sine to the 2 cosine to the 2, no, let me do another thing. So here I factor 1 over cosine here, I factor this out, so then what happens? It becomes equal to 1 over cosine to the 2 theta, then I will have 1 plus sine theta, and in the denominator I will have similar thing. Okay, now it becomes sine squared theta 1 plus sine theta divided by cosine to the 2 theta, and then I will have 1 plus cosine theta. Yes, but this sine squared here, I can write it as, if you compare this one, it is not finished yet. So you see here what I need, this is my k value. So it is not, I have 1 minus cosine alpha, 1 minus sine alpha. Okay, but here I have positive signs, so that's not a big problem. So what can I do? Instead of sine squared, I can write 1 minus cosine to the 2 theta, 1 plus sine theta, divided by, instead of cosine squared, I can write 1 minus sine squared theta, 1 plus cosine theta. But using the quadratic pattern, using the conjugate pattern, I can factorize these two expressions. Then I will get 1 minus cosine theta, 1 plus cosine theta, 1 plus sine theta divided by 1 minus sine theta, 1 plus sine theta, and then 1 plus cosine theta. Yes? So then this one and this one are simplified. This one and that one are also simplified. So what is left is exactly this part that I really need that. So this becomes 1 minus cosine theta divided by 1 minus sine theta. So the k value is exactly this one. But of course here, in principle, I should have replaced theta with alpha from the beginning. Okay, so that's not a big deal. Yeah, I can just do it right now. So this becomes 1 minus cosine alpha, 1 minus sine alpha. And that is exactly what is here, what is demanded here in this part. Okay, now the last part of the problem is find and simplify an expression for the minimum value of L in terms of alpha. So what I need to do, I need to plug this value for K inside here, yes, but everything should be written in terms of alpha. And then the point is that you are not supposed to calculate L in terms of your constant, which is more natural. The problem has demanded to calculate the parameter, the minimum parameter, in terms of alpha. So this is what you need to pay attention to. In principle, we should solve the problem and write this in terms of k, not the alpha, yes? Because alpha, even though I have a relation for my alpha, but we haven't calculated that alpha yet. Okay, but the point here is that we have to write everything in terms of alpha. Okay, so what I'm going to do, I have this formula, I plug this k here and try to simplify as much as possible. Yes, this is my goal. Okay, so let me, so how much do yes, I have enough space hopefully, but because I want you have this one in front of our eyes, let me just copy this one again and bring it here. So yes, so I put it here so that we can see that. So what I'm going to do here, first of all, I replace theta everywhere with this alpha, and then I replace k with that expression and try to simplify that. Yes, so I would write that L minimum is equal to 1 plus cosecant of theta is 1 over cosine of theta, but I was supposed to write alpha. And then this becomes sine theta, which is sine over, tangent of theta, which is sine over cosine, so I would write this. And then I have, instead of k, I plug that expression in. And then 1 plus, instead of cotangent, I would write cosine alpha, sine alpha. And instead of cosecant theta, I would write 1 over sine alpha. Yes. So I can write it as 1 plus, for example, I can take the common denominator here, the common denominator here. So this becomes a cosine alpha, 1 plus sine alpha. And then I multiply this expression in, but before that I can just take the common denominator here, so let us do it in this form. So it's 1 minus cosine alpha, 1 minus sine alpha, and then I have 1 plus 1 plus cosine alpha divided by sine alpha. So this becomes 1 plus sine alpha over cosine alpha. And now I multiply this expression here, which becomes the same, and then I multiply this expression here. So this becomes 1 minus cosine alpha, 1 minus sine alpha, and then plus 1 minus cosine alpha, 1 plus cosine alpha, divided by sine alpha 1 minus sine alpha. Yes, but this expression is 1 minus cosine squared alpha, which is sine squared alpha, and then one of these sine alphas and this sine alpha are simplified. So what I get is 1 plus sine alpha cosine alpha plus 1 minus cosine alpha 1 minus sine alpha, and finally I will get sine alpha divided by 1 minus sine alpha. Yes. Now this is something we have to simplify, so I think the common denominator is probably a good choice. So if you don't mind, let me go below. So this becomes cosine alpha 1 minus sine alpha as the common denominator. So the first one becomes this. The second one just becomes this. Yes. The next one becomes cosine alpha times 1 minus cosine alpha. And finally, the other one is sine alpha cosine alpha. Okay, so let us see how it goes. This expression is 1 minus sine squared alpha, which is cosine to the 2 alpha. Yes, so let us multiply things in now. So this becomes cosine alpha minus cosine alpha sine alpha plus, so you see I multiplied this, and instead of this expression I can simply put cosine squared, so it becomes cosine to the 2 alpha. Then I multiplied this, it becomes cosine alpha minus cosine to the power of 2 alpha, and then finally I have sine alpha cosine alpha, and then I have divided by cosine alpha 1 minus sine alpha. Hopefully I can fit everything here. This cosine to the power of 2 with negative sign and that one are cancelled. This one and that one is also cancelled. So what is left is 2 cosine alpha. Yes, I have a cosine alpha here and a cosine alpha there. So then it becomes this expression. And finally, this becomes 2 over 1 minus sine alpha. So let us write here. So L minimum is equal to 2 over 1 minus sine alpha.